Hey everyone, welcome back to another MCAT ACE lecture, and in today's lecture we are going to look over UV-Vis spectroscopy and conjugation and how these two play into one another, and we're going to take a look at conjugation and sort of understand not just what it is, but how we could also predict some nanometer lambda max values from UV-Vis based on that. So let's go ahead and take a look at our outline. So the general outline for what we want to cover here, number one, what is UV-Vis spectroscopy? And we'll take a look at that in reference to the electromagnetic spectrum. How does UV-Vis spectroscopy actually work? That involves some HOMO to LUMO transitions, so we'll be talking about molecular orbital theory a little bit. Electron excitation and Beer's law when we're looking at absorbance and concentration relationships. We'll also discuss briefly lambda max, which is what we're going to be using for optimal absorbance. And then when we get to the conjugation section, we want to define what a conjugated system is. This is mostly in the context of organic chemistry. And we will examine an example of a conjugated system with UV-Vis. And then we will take several other conjugated systems and compare them to the initial example and see how that plays out. So it's going to be very important that we can conceptualize the effect of conjugation and how it interacts with UV-Vis spectroscopy. And then obviously we'll have our practice problems at the end. So what is UV-Vis spectroscopy? So the UV-Vis is referring to ultraviolet and visible light in the section of the electromagnetic spectrum where those would be found. So the energy that's going to be associated with wavelengths from this region are usually used to excite electrons up to a different orbital. Now, there are other types of energy along the spectrum that we have discussed in some of our other lectures. So for instance, when we discussed IR spectroscopy, that's the infrared portion, and the IR has enough energy to vibrate bonds, but not to excite electrons into different orbitals when we're dealing with bonds. Okay, something like microwaves has enough energy to rotate molecules, but not to actually excite the electrons. So as you go back and forth along this spectrum, the energy values that you're going to find have different capacity. So when you get up to something like X-rays, you can actually start ejecting electrons completely from a given compound. So you can see here in the middle, we have the visible light. Visible light that we actually see with our eyes is a very, very narrow sliver of the electromagnetic spectrum. And it goes from about 400 nanometers to 700 nanometers. So 400 on that lower end is getting closer to the ultraviolet. Those would be your purples, blues, things of that nature. Then you move up through the greens and yellows. And then on the other end, you have orange and red, red being closer to the 700 mark, and then red would start to, as the name would infer, bleed into the infrared spectrum, or the IR. So we are mainly going to be focused on UV and visible, which is in this portion right here. So the UV, the ultraviolet, can start at around 10 nanometers, and it goes up to about, it's a little less than 400, so around 380 or thereabout. Then you start transitioning into violet, and then you go all the way up, violet being 400 all the way up to the red, which is 700, and then you start moving to the infrared. So, in terms of UV-Vis spectroscopy, the energy in the UV-Vis region is going to be passed through a solution. So most commonly this is going to be a cuvette or maybe some sort of a test tube. There are sort of basic ones that get used in general chemistry labs where you can just insert a test tube. But usually it's going to be a cuvette that's got the clear sides and the arrows that you line up. You put your solution in that. You put it into the instrument and close the lid, and then it's going to basically scan through a bunch of different wavelengths, and you will find the optimal wavelength, which is known as the lambda max, which is where you're going to hit the best absorption of that light so it doesn't come through to the other side of the detector. And once you have your lambda max or your optimal wavelength, that is what you set the instrument to. So then instead of doing this large scan through, it would go ahead and set the wavelength to exactly the number that you want. That would go ahead and shine through the sample, and then the sample, based on the amount of the given compound in the sample, will absorb that light, and only a certain amount will be able to pass through. And that's the general premise behind this, is when we're absorbing a certain amount of light, the detector can pick up what remains, and we can directly relate the absorbance of that light that's exciting the electrons to concentration. And I also want to mention there is a technique called fluorescence. Fluorescence is just the opposite end of this. So whenever you excite an electron up to a given orbital, it also has to come back down and go back into the ground state so that it's stable. And that is the process of fluorescence, when you've excited it and then you're measuring the energy that's coming back down off. That would be fluorescence. So, a little bit more in terms of how this works. You have your HOMO and your LUMO transitions. Now, what does this refer to? So, in UV-Vis, we're going to utilize a lot of MO theory. And this is, for those that may have taken a course that uses MO theory, this is molecular orbital theory. So, molecular orbitals are formed, okay, by individual atomic orbitals of bonding atoms. So the most simplistic version of MO theory that most students start with is a hydrogen-hydrogen bond, because you only have those two s orbitals, and they come together to make a sigma bonding orbital and a sigma anti-bonding orbital. And then you can get more and more complex from there as you bring in p orbitals. You also have different levels, so once you go past quantum level 1 or shell 1, you start getting a lot more in terms of your molecular orbitals. So keep in mind the term molecular. When we're dealing with molecular, you're talking about a molecule, whereas the atomic orbital is stemming from the individual atoms. Those are your s orbitals, your p orbitals, and so on. All right, so when we examine a molecular orbital, we're going to look at what's called the HOMO and the LUMO, and those are used to explain the electron transitions. So these terms, HOMO refers to the highest occupied molecular orbital. So when I draw out my MO, or my molecular orbitals, the one that has the highest rank that still has electrons filled in it, that would be considered the HOMO orbital. And then the LUMO is going to be the lowest unoccupied molecular orbital. So that will be, as I go and I continue to climb, the next rung up, where I do not see any electrons right above the HOMO orbital. That would be considered the LUMO orbital. And the electron is going to go from the HOMO to the LUMO orbital when it is excited. That's the shortest, or the path of least resistance there for an excitation. So this sort of represents it as a diagram. You may have seen something like this in a course before. So you have your energy that's running along this y-axis here. And as you climb up, similar to when we did 1s, 2s, 3s, so on and so forth, as you climb up, you're going to be increasing in energy. So we always fill our electrons in the lowest energy state. And you can see those at the bottom here. And then I've labeled in blue the HOMO orbital here, which is going to be the one that is highest in energy that is occupied. And then the LUMO, which is in purple here, is going to be the lowest one that is unoccupied. So I have two unoccupied orbitals here. The one that is the lowest in energy that is unoccupied is going to be considered the LUMO. So then you allow the UV-Vis energy to come in and hit your compound, and whatever molecule you have, it will excite one of the electrons, provided that you have the correct wavelength here. It will excite one of the electrons from the HOMO into the LUMO orbital, and that is the general premise behind how UV-Vis spectroscopy works when you get ready to excite electrons. So in terms of measuring absorbance, once we have passed light through the sample in a spectrophotometer, the detector on the other side is going to determine the amount of light that is passing through the sample. Now, usually, when most people start learning this, they use absorbance. However, it is possible that you can use the inverse, which is percent transmittance. And some people prefer to use percent transmittance. It's just a logarithmic transformation between the two, and they are inversely related to one another. So if you're talking about absorbance, meaning the amount of light or energy that is being absorbed, okay, the transmittance is how much is getting through on the other side to the detector. So the absorbance values can be directly related to the amount of compound that's present in the sample, because the more compound you have, the more ability to absorb that light, and therefore you can relate it back to the amount in the sample or the concentration. And that is done through using the Beer-Lambert law. Sometimes it's just known as short as Beer's law. So the Beer-Lambert law is what we have outlined right here. Its absorbance equals, and you can see it's epsilon times L times C. So what do all of these mean? Well, the ABS is the absorbance. The epsilon is the molar attenuation coefficient. It's sometimes called the extinction coefficient. This is basically a measurement of how well a given compound is going to absorb the light at its lambda max, because that can vary from compound to compound. Okay, L is the path length, and this is referring to the width of your cuvette, test tube, whatever you are actually passing it through. So the amount of liquid that's in there, okay, it's going to fill up the vessel, whatever you're using, usually a cuvette, and that path length, or the width of that cuvette, is going to be important because that is what the light has to actually pass through as it's being absorbed by the compound. Most of the time, not always, but most of the time, it is going to be 1 centimeter. And when it's 1, that drops out of the equation, because when you multiply anything by 1, you're just going to get that value back. And then C is the concentration. So you can see mathematically here, the absorbance is going to be directly proportional to the concentration. So as I increase one, I would increase the other. And that makes sense, because as we were saying, the more of a given compound you have in your solution, the higher the absorbance is going to be. It's going to be able to absorb more and more of that light that is attempting to pass through. So now we're going to shift away just a little bit, since we have an understanding of UV-Vis, and we're going to talk about conjugation and what conjugation is. We'll tie it back into MO theory, and then we will sort of tie it all together and discuss how conjugation works with UV-Vis. So in chemistry, when we talk about conjugation, this is when we're going to have multiple atomic orbitals that are overlapping with one another. Usually, most of the time, especially in organic, we're going to be talking about p orbitals. Now, it is possible with d orbitals and things like that. However, p orbitals are the most common when we're talking about pi bonds, especially in organic, because carbon can only use p orbitals. It's not going to have d orbitals. All right, so when you have multiple p orbitals that overlap with one another, that is going to allow for electron delocalization, or a spreading out of electron activity among multiple atoms. And if you remember from your organic coursework, when you have delocalization, which is tied in with resonance, okay, that is a very stabilizing factor. So this is a good thing for compounds to have as far as their energy is concerned. Now, when you are looking at something on paper and visually examining it, you want to look for a pattern where you have pi bonds, sigma bonds, pi bonds, okay? Or some people use this and refer to it as the double single double pattern. That's a little bit generic, just because you could have a triple bond, and a triple bond would also count towards this type of pattern. But you're essentially looking most of the time at double bond, single bond, double bond. So some examples you can see here are 1,3-butadiene. This is a very common molecule that is typically discussed at the beginning of your Diels-Alder reactions and your conjugated diene chapter. And then benzene is another very well-known compound in organic chemistry. You've got the alternating double bonds in the ring structure, and a lot of times when this is drawn out, instead of drawing the alternating bonds, there's just a circle that's drawn in the middle of the ring. And when we draw a circle in the middle of the ring, what you are representing is that the electrons are in constant flow or motion. They're being delocalized over every single p orbital involved here. It's not just at individual nodes. All right. So, conjugation in relation to molecular orbital theory. Let's take a look at 1,3-butadiene. So when we take a look at 1,3-butadiene, you can see drawn out here the p orbitals. So every time we have a pi bond exists in a p orbital. So this gets a little bit out of MO theory and a little bit into valence theory, the Vesper theory. And it talks about when you have overlap for sigma bonds, those are going to be from hybridization, so sp2, sp3, things of that nature. But when you're going to have pi electrons operate in p orbitals and d orbitals, okay? So the p orbitals have to be left behind, and that's why whenever we have double bonds, usually they're going to be characterized as sp2, because the hybridization process has to leave a p orbital behind for the pi electrons to hang out in. All right, now, so we have 4 p orbitals here, and because we have 2 pi bonds, we have a total of 4 pi electrons, because remember, 2 electrons to a bond. So 4 p orbitals and 4 pi electrons in 1,3-butadiene is going to lead to these 4 p orbitals, all equal in energy, and each one of them gets 1 pi electron placed into them. Okay? Now, when we get ready to look at this from an MO perspective, we take these and we create what would be the bonding and the anti-bonding orbitals. So the lower 2 orbitals here would be the bonding orbitals, and the higher 2 would be the anti-bonding orbitals. You can almost draw a line right in between here that separates them in terms of energy. So when we have this, we have 4 pi electrons, they are going to fill up the bonding orbitals. And that is because those are lower in energy, and just like when we do the Afubao principle and Hund's rule, we always want to pair them up and go from the lowest energy to the highest energy. Now, this is what it would end up looking like for 1,3-butadiene. So what I've done here is we have the 1,3-butadiene with its HOMO filled and the LUMO is empty, and 1,3-butadiene has an excitation lambda max at 217 nanometers. So if I were to take this compound and I were to put it into a UV, and when I close the detector, I put it and set it for 217 nanometers, it would be able to use that wavelength, hit the compound in the cuvette, and what I would see is that the HOMO and the LUMO here would have a jump or an electron transition. And you see in green here, I have highlighted what's called delta E, which is the difference in energy between the HOMO and the LUMO. This is the energy that is going to be associated with the wavelength, the 217 nanometers that's coming through. Because remember that wavelength is in relation to energy, and we'll take a look at that equation in a minute here. All right, but this is exactly what's going to happen. You're going to take the 2 electrons that are found in that HOMO orbital, and you're going to pop one up to the LUMO when you hit it with the 217 nanometers. And that difference in energy is going to be directly related to the 217. So a lot of this gets into discrete quantum values when you're talking about you need an exact energy in order to excite an electron and do this jump. Remember, electrons don't hang out halfway in between orbitals. They either stay in the orbital they're in, or they have enough energy to jump to the next orbital. But there's nothing in between when we talk about discrete quantum mechanics. Okay, now let's relate the wavelength to energy, which is what we were just discussing a minute ago. So energy can be inversely related to wavelength. So you can see energy here, which is also equal to Planck's constant times frequency, all right? However, we can bring that further out by saying energy equals Planck's constant times the speed of light divided by lambda. So energy and lambda have an inverse relationship to one another because lambda is in the denominator, and lambda being wavelength when we're talking about that. That's the abbreviation used. So as the energy gap between the HOMO and the LUMO decreases and shortens, the required lambda value for an electron excitation is going to increase. That doesn't mean the energy increases. The energy is getting closer and closer. The delta E is closing in. But because they're inversely proportional, as the energy gets lower and lower, the lambda max, the wavelength, is going to get larger and larger. Okay? So this statement that's outlined at the bottom here that I'll read through in a second, this is the line of thought or process here. Because conjugation and electron delocalization is a stabilizing phenomenon, the more conjugation a system contains, the narrower the HOMO-LUMO energy jump, meaning the energy requirements are getting smaller and smaller, and then the higher the lambda max becomes. So, if you can understand that and hold that in your mind for a minute, take a look at this. Here is the lambda max for several conjugated systems. Now, the first one is not conjugated because I want to prove my point as we add conjugation. All right? So the first one is just a pi bond. It's not in conjugation with any other type of p orbitals. It's at 174 nanometers. And then as I conjugate to 1,3-butadiene, I get 217 nanometers. And then I can continue the conjugation pattern. I go to 258 for the triene, and the tetraene goes to 290. And then this structure that's outlined down here is beta-carotene. Okay, so beta-carotene is a huge conjugation setup. And it has 455 nanometers as the excitation wavelength for lambda. Now, if you think about beta-carotene we associate with carrots and a lot of these other types of fruits or vegetables, sweet potatoes. It's got an orange color to it, all right? But you have to think carefully, because if it's showing an orange color, that does not mean that it is absorbing orange wavelength or orange light, because if it was to absorb it, it wouldn't be shown back to the human eye. So whatever it's absorbing, if you look at a color wheel or you look at the complementary color, okay, I don't know if you guys have ever drawn a color wheel. You draw a color wheel with the 6 primary colors, and you do your red, orange, and you go all the way around until you get to violet, okay? And when you do that, if you look at the opposite complementary color, that is the approximate wavelength that you will be absorbing, or the type of light that is being absorbed. So orange has a complementary of a blue-violetish color. And because of that, if you see something with your eye that looks orange, that means it is absorbing at the blue to violet region. And that makes sense, because when we were discussing the electromagnetic spectrum at first, we said on the lower end towards the UV, which was around 400, was where we saw the violet, and then the blue was a little bit higher. And then 700 on the other end was the red. So if we're talking about 400, 450, anywhere in that region, you're talking about the violet bluish region, which is what beta-carotene has here. And because of that, it's absorbing the violet blue, and it is reflecting, or it is showing, transmitting, the orange color, which is what we're picking up, and that's the complementary color to that violet or blue. All right, so that is how this works. When we start looking at conjugation, as conjugation increases, it's going to increase the wavelength where we see the absorbance. And because of that, it's also stating that the energy between the HOMO and the LUMO is decreasing. There's a smaller and smaller energy jump that has to be accomplished as this number is climbing up. Because remember, as we go along the electromagnetic spectrum, the wavelength, right, is inversely proportional. It's getting weaker and weaker. So something that's 217, that's very squarely in the ultraviolet region. And then something that's 455, that is something that is getting into the visible region. And then above the visible region, if we went all the way to red, then you'd start getting into the infrared. That gets even weaker. Then you can only start vibrating bonds, and so on and so forth. All right, so that wraps up conjugation, as well as UV-Vis spectroscopy and the general premise behind how it works. So we are now going to go ahead and head over and look at some practice questions. Okay, so I have brought up the practice problems here. We're going to go through them as usual. Take a look at them. I'll scroll through them one more time slowly so you can pause after that, and then we will work through them together. So get as far as you can with these questions before unpausing the lesson and continuing with the walkthrough. So number 1, the UV visible spectrum of NADH displays a lambda max at 340 nanometers, whereas NAD+ is transparent in this spectral region. What chemical feature permits the progress of enzymatic conversion of pyruvate to L-lactate to be monitored via UV visible spectroscopy analysis? All right, so what I have here is the outline general reaction. You can see the pyruvate with the NADH, and then you can see the resulting L-lactate and the NAD+. So here are the options, and you want to listen and read over these carefully. A. Absorption at 340 nanometers in the UV visible spectrum begins to appear and then gradually intensifies as the reaction progresses due to the conversion of the pyridine ring in the NADH into the corresponding 1,4-dihydropyridine moiety in NAD+. B. The absorption at 340 nanometers in the UV visible spectrum begins to appear and then gradually intensifies as the reaction progresses due to the conversion of the 1,4-dihydropyridine ring in NADH into the corresponding pyridine moiety at NAD+. C. Absorption at 340 nanometers in the UV visible spectrum gradually becomes less intense as the reaction progresses due to the conversion of the pyridine ring in NADH into the corresponding 1,4-dihydropyridine moiety in NAD+. D. Absorption at 340 nanometers in the UV visible spectrum gradually becomes less intense as the reaction progresses due to the conversion of the 1,4-dihydropyridine ring in NADH into the corresponding pyridine moiety at NAD+. So a lot of that sounds repetitive. What you want to look at here, the main differences, is that two of the options are talking about the 340 nanometer spectrum begins to appear and then it intensifies in A and B, or in C and D, it doesn't intensify but it becomes less intense. Okay, so that's one point. And then the second point is you need to pay attention to where it says the NADH corresponding to, okay, and the NAD+ corresponding to, because it's talking about the pyridine ring and the dihydropyridine ring. So you need to make sure you're paying attention to which structure is correct for which one. All right. Number 2, the visible spectrum of cobalt hexafluoride 3-, the ion, an octahedral complex absorbs light at lambda equals 700 nanometers. With the reference to the color wheel shown below, what color will be perceived by the eye for this structure? So keep in mind what we discussed with beta carotene, because that can help you in this problem right here. All right, so there's your color wheel, and again remember that the cobalt complex is going to absorb at 700 nanometers. That's where it absorbs light. So the question is asking, what color will the eye be picking up, okay, out of the color wheel here? And the options are red, blue, green, or violet. All right, and then number 3, a compound is known to have a molar absorptivity constant of 5,500 in acetone. If an acetone solution of the compound was placed into a 1 centimeter cuvette and the absorbance is found to be 0.750, what is the concentration of the solution? And you see your options down there. All right, so I'm going to go ahead and scroll through these one more time. I'm going to go slowly, especially in this first part, in case you need to pause it to analyze any of the answers that are down here. Okay, and as we said before, go ahead and attempt these to the best of your ability. If you get stuck, go ahead and unpause the video so that you can go through the walkthrough and see how we work through this. All right, so go ahead and pause the video now, and I will see everybody in just a second. All right, so hopefully you had a chance to work on these. We're going to go through these now. For question 1, if you take a look here, it says the absorption at 340 nanometers in the UV visible spectrum begins to appear, and then gradually, and we have to decide whether it intensifies or it becomes less intense. Well, let's go and look at the question itself. It says the UV visible spectrum of NADH displays a lambda max of 340, whereas NAD plus is transparent. So this is important here. The fact that NAD plus is transparent means that the absorbance is lowering, it's going away, and the light is able to shine through the solution. So we would not expect it to be more intense. We would expect less intensity over time until it becomes transparent. And because of that, both of the options that have gradually intensifies are going to be off the table because that is not what's going on here. So we're left with C and D at this point. So now the real question is, once we know that it's going to become less intense over time, we want to match up the proper structures. Okay, so a pyridine ring is going to be a structure that has something that looks like this. Okay, and then the 1,4-dihydropyridine moiety is going to be the other portion that we saw that has something more along the lines of this. All right, so if we come up here and we look, the NADH appears to have the 1,4, and the NAD plus appears to have the pyridine. So this is the 1,4, the NADH, and the NAD plus is the pyridine. So of the two options, we would want to make sure that we select conversion of the 1,4-dihydropyridine ring in NADH. That's correct, because we just said NADH is the 1,4. And then into the corresponding pyridine moiety at NAD+, and that's correct because the NAD+ up here has the pyridine moiety. So D is the best selection out of the bunch here, and that's what we would be looking for. All right, so number 2, the visible spectrum of the cobalt hexafluoride ion is going to absorb at 700 nanometers. So we want to find out what color would be perceived by the human eye when we're looking at this. So remember when we were discussing beta carotene absorbing with the violet and the blue, we were talking about the fact that beta carotene is normally orange. So you're looking at the opposite on the complementary color wheel. So right here, 700, the closest to that is red. Right here, 680 is where red starts and it goes up to about 700. So if we were to take a look, the opposite complementary color, you want to go directly diagonally across, would be green, around 530. All right, so this structure would be absorbing at around 530, which means that we would see green. I'm sorry, it would be absorbing at 700. What's being reflected, what our eyes would be seeing, is the 530 nanometer wavelength, and that would be green, is what we would perceive. So C would be the correct answer there. And then number 3, a compound is known to have a molar absorptivity constant of 5,500 in acetone if the acetone solution was placed into a 1 centimeter cuvette and the absorbance is found to be 0.750. What is the concentration of the solution? This is pretty straightforward. You want to use the Beer-Lambert law. So it's going to be absorbance equals the constant, which is represented by epsilon, times L, which will be the path length, times C, which will be the concentration. Now, what we're trying to find is the actual concentration here. So the values that we were given, 0.750 is the absorbance, equals 5,500. That's the molar absorptivity constant. Okay, and then the path length is 1 because it's a 1 centimeter cuvette. And then we're finding concentration, right? So the 1 is going to drop out. We don't need to worry about that. So all I really have to do here is some simple algebra. The concentration is going to equal 0.750 in the numerator, and in the denominator I divide through by 5500. Okay, keep in mind this centimeter would cancel out with the centimeter that's there for the 1. All right, and then what you end up with is a concentration. And if you plug this in to a calculator or you get a rough estimate of it, you should find 1.36 times 10 to the negative 4th molarity. And that is the best option here. Okay, so that wraps up the question portion of the UV-Vis spectroscopy lecture. So hopefully everybody found this information useful and you were able to apply it during the problem-solving practice session. And we will see everybody for additional lectures with content for practice for the MCAT ACE course.